So we'll continue our discussion about quantization. Okay? We learned about pruning, and then this is the second technique we learned about compressing neural nets. So we will first review about the linear quantization that we learned in the last lecture, and then we're going to introduce these post-training techniques, which is super important. If you have an iPhone, you have an Android, running certain neural nets on your phone, it's very likely that either one of these algorithms is running locally on your phone. Okay? So that you can deploy your models using integer. So very important concept. We'll introduce how to quantize the weight, the activation, and also the bias. Right? And then in order to fine-tune and recover the accuracy loss due to quantization, we'll introduce Quantization-Aware training, QAT, okay, to recover the accuracy. And then we're going to introduce binary and ternary neural nets to see how can we further reduce the number of bits to only 1 or 2 bits. Lastly, we'll talk about mixed precision quantization, which is very popular these days. You can have a mixture of 4-bit, 8-bit, 16-bit for inference. Okay? All right, so let's first review what we have learned so far. We've talked about different quantization schemes from floating point versus integer weight, floating point codebook versus fully integer weights. Okay? We've talked about k-means based or linear-based quantization, where k-means quantization first cluster the weights according to their number, and have this non-linear centroid codebook. Okay? The centroids are non-linear, so you have to decode it to run it in. Actually, the inference is still done in floating point. You just save the storage, but it just doesn't save the inference status. Okay? This is showing how much we can compress by combining quantization with pruning. Okay? And reduce LXN to very tiny little, like 3% of its original value. And then we talk about linear quantization, okay? To have this linear code book, okay? -2, -1, 0, and 1 for 2 bits. We introduced this I-fine transformation to transform this quantized value to this real value, okay? Which include a 0 point, okay? And also a scaling factor. And the most important part is how to determine this 0 point, okay? And also how to determine this scaling factor. Okay? So in the last lecture we introduced these concepts, but in this lecture we're going to introduce how do we decide what is the 0 point and what is the scaling factor. Okay? And how do we decide that for the weight, for the activation, and for the bias. Okay? So remember, this linear quantization is basically mapping from this like 0 to 255 all the way to this from this R min to R max. Okay? So if we have 2 bits, the Q min and Q max, which is the quantized domain, corresponds to -2 and +1. If you have 4-bit, then that's -8 and +7. Okay? And then we went through the equation in last lecture. Given a 14-point matrix, but a linear layer, okay, a fully connected layer, how do we derive the quantized version for that? And what are the assumptions? Right? So we assume the 0 point for the weight is 0. The 0 point for the bias is also 0. Okay? So which simplifies the calculation. And we have this scaling factor of the bias equal to the sum to the multiplication of the scaling factor of the weight with activation. And finally, we have the bias, Q bias. We define Q bias to be this term. Okay? So finally, we can just fully calculate the majority of the weight lifting of the computation in fully integer multiplication. Okay? And accumulate that using 32-bit integer add. Okay? Finally, we have this scaling factor, which can be done by shift, and also together with integer operations. Okay? And finally, n-bit integer add. Okay, should be good. Okay, sorry for those who's watching on YouTube. Hopefully now it's better. So for convolution neural nets, we can simply change the convolution change it from matrix multiplication to convolution, and then the rule of thumb stays the same. So let's review this example. How do we determine the scaling factor? Okay, the scaling factor is determined by the ratio between the range of the floating point versus the range of the integer value. Okay? So in this case, R max, this is the R max. This is R min, the largest and smallest value. And Q max and Q min is basically 1 and minus 2, since we have 2 bits, that's fixed. So we can calculate the scaling factor. And we can further calculate the 0 point using this equation. Okay? So R min, this is the R min, and S, we plug in this scaling factor to get the 0 point. So for the symmetric case, where 0 point has to be 0, okay, so the scaling factor becomes the max number of the absolute value divided by the Q max. Okay, so 2.12 divided by 1. Okay, so that's the scenario corresponding to symmetric quantization. Okay, so this is asymmetric, where we have a 0 point. And this is symmetric, where 0 point is basically 0. So in this lecture, we are going to talk about how do we determine these hyperparameters, okay? The 0 point and also the scaling factor, including the weight. How do we determine the Z and S for the weight, for the activation, and also for the bias. Okay? So let's get started with the weight to begin with. Okay, so the R max is basically the largest value in your weight. Okay? So the problem is that for different channels in this figure, how many channels do we have? 1, 2, 3. We have 3 channels. Okay, for this EN, we have 3 channels. And it's showing in this figure, the range for different channel can actually differ a lot. Right? So if we do such per tensor quantization, just use a single scaling factor for the whole weight tensor. What is the problem here? So this is for different channels. This is the range of the weight for each layer for different output channel, for different channels. So this is for just one layer for different channels. Calculate the range.
The range of each channel is definitely not uniform, so you can see a scaling factor, but maybe some issues for certain layers that are outliers in their size.
Yeah, exactly. So we will expect a significant drop of accuracy if we just use a single scaling factor and a single bias for all the channels. Right? So the solution is to use this per channel quantization. Okay, we give a specific scaling factor and bias for different channels. Okay, so let's see an example. With our familiar 4x4 matrix, this is the IC dimension, this is output channel dimension. Okay, so we are comparing this per channel quantization versus the per tensor quantization. So with per tensor quantization, we first have this R max, which is the largest value in this matrix, okay, 2.12. And then we can calculate the scaling factor according to our equation, the max of the floating point range divided by the max of the integer range. Since we have only 2-bit, the integer range is from -2, -1, 0, and 1. So this Q max is 1. So the scaling factor is 2.12. And then we are going to quantize the matrix according to their value, and this is a reconstructed number. Okay? As you can see, this 2.09 is quantized to 1, okay? And this minus 1.03 is quantized to 0, okay? Because this number divided by this number is actually closer to 0. Okay? So therefore, it is quantized to 0. And then we can recover to reconstruct the weight matrix by multiplying this quantized weight with this scaling factor. Okay? So this is the quantized weight. And if we calculate how much difference is that from the original weight matrix versus the reconstructed weight matrix, So it's actually 2.28. Okay. What if we use per channel quantization? So for each channel, we can calculate its R max. In this case, the largest value in the first channel is 1, 2, 3, 4 numbers, is 2.09. And then for the second channel, it's actually 2.12. Okay? So we have different scaling factors. So this one is actually 1.92. For the last one, the range is a bit smaller, so the scaling factor is also a bit smaller. So how do we quantize in this case? So we have different scaling factors. Okay? So this is the quantized matrix. Okay? So if you compare the per channel quantized value versus the per layer quantized value, did you guys observe any number is different?
In the last column, second last row,
Yeah, this one is -1. This one is 0. And guess why is that the case? Corresponding to this -103.
The scaling factor is different.
Right, the scaling factor is different, right? So if I use the per channel, I'm going to divide the scaling factor, which is 1.92. Okay, so this number divided by 1.92 is actually smaller than minus 0.5. So it will be rounded to -1. Okay? But if this number, minus 1.03, divided by this scaling factor, it will be larger than minus 0.5. So it will be rounded to 0. Okay? So that's the subtle difference where per channel and per layer, per tensor quantization can actually lead to different quantized value. Okay? And let's reconstruct the original matrix using the per channel method. And we can see the first row, the second row, they actually have different scaling factors, that's different value. Okay? And the reconstruction error, which is original weight matrix minus the reconstructed one, is 2.08, which is smaller than the original per tensor quantization. Okay? So this is just illustration about the difference per channel versus per tensor quantization. Per channel is more complicated, but give you more flexibility and and smaller reconstruction error. If hardware can support this, then absolutely this can lead to better accuracy. Okay. So here is the summary. So the drawback is that not all hardware may support it, and also create unnecessary overhead. For example, you have to store each channel. You have to store a different scaling factor. Okay, create some overhead. But if the tensor is pretty huge, it doesn't matter if you have just one number for the entire channel. Okay, so usually this is a trade-off. And nowadays, actually, such per channel quantization is very popular in TensorFlow, in PyTorch, in mobile deep learning, or microcontrollers. We've been all using this per channel quantization these days for lots of the vision models. Okay? So the next question is that since there is some overhead on the hardware, the natural question is, can we have the best of both worlds? Right? Can we have the per tensor quantization still have lower difference and have a higher accuracy? Okay, so that's our next question. Can we make the weight ranges similar to each other, okay, for each channel? Make it similar to each other so that even such per tensor quantization, you have just one scaling factor for the entire tensor, still work well. Okay. So this is something that's highly imbalanced. Like this channel has a pretty huge mean as max range. But after this thing called weight equalization, which we are going to introduce, we want to have it something roughly similar range. Okay. So that's the next thing we're going to learn, which is weight equalization, a very cool technique invented by quantum folks. Quantum is very big in this area for this quantization work, very cool work, trying to equalize the range for different channels. Okay, so imagine we have two consecutive layers. Okay, this is the ith layer. This is layer I plus 1. Okay, and this is the output channel dimension. This is the input channel dimension. Imagine we have the row of the ith layer versus the column of the I plus 1 layer. If I divide it by 2, if I multiply this by 2, if it's a linear layer, then what is the effect? It's the same. Right? Since for matrix multiplication, if I divide this by alpha and multiply this by alpha, then the result is the same. Okay? So actually, I can use this feature try to equalize different channels. For example, this is for layer I plus 1, and I plug in this x I plus 1 to be f, and this is the ith layer. I just plug in ith layer into x I plus 1. And if f is linear, then I can scale wi plus 1 and then scale down wi. Okay? So if it is linear, then the final result is actually the same. So actually, I can use this characteristic to equalize different layers. Okay? So I define the scaling factor like this. So it looks complicated, but actually it's quite simple. So I just have a scaling factor for the ith layer corresponding to the output dimension. Okay, output dimension equal to j. Okay, so I is equal to j for I plus 1 layer. Okay, so this is layer I plus 1, and this is the jth column. Okay, that's why we have this IC equal to j. So IC actually corresponds to the input channel. Okay, OC corresponds to this output channel. So for layer I have this OC equal to j. Okay, finally, I have this IC equal to j, I plus 1 layer. So what if I for layer I divide it by s, and for layer I plus 1, I multiply it by s. Okay, so this is the original value for ith layer. Okay, so this is jth row. Row is corresponding to OC. Okay, so this is this term. And since s is defined like this, I just plug this in. Okay, so this denominator comes to the denominator. This denominator comes to a denominator, and then I can find it's just multiplying this OC and IC for these two layers and have the square root of that. Okay? The way intuition is like if layer is 1, the other layer is 100, then you just may as well make them both of them to be 10. Okay? Since 10 plus 10 equal to 10 multiplied by 10 equal to 1 multiplied by 100. Okay? That's the roughly the intuition for weight equalization. And similarly, you can plug in layer I plus 1. Okay? So this is original j's column of layer I plus 1 corresponding to here. Okay? J's column of layer I plus 1. And you multiply by this scaling factor, which is this. So you plug this in. Part of this gets cancelled, okay? So you can get a final result is also for the ith layer, I plus 1 layer, multiply them together, having the square root of that. Okay? So after this weight equalization, we can roughly make the different channels of each layer to be roughly the same. So what is the limitation for this method?
You have to do like 2 at a time and just keep doing it, keep making passes through, because there's no guarantee that the first layer and the last layer will be anywhere close to each other after one pass.
Yeah, you have to do this propagate from the entire network. Every time you have to do 2 layers at a time. And also, and assume the layer is linear between the two layers, right? So if you use complicated activation function like sigmoid, this may not hold. But if you use this simple nonlinear function like ReLU, right? It doesn't change your sign. If it is positive, then it's still positive. It works quite well for ReLU activation function. Okay, since you have the assumption that f here should be linear. Okay, so pay attention if you don't have such ReLU activation function. And is this does it require any training? Doesn't. Right? It's like static. You can just get the weight directly, equalize the weight without any retraining. Okay? So it is pretty much very low computational cost. You don't have to do any retraining. Doesn't require you to find any training data, any images. So the way I remember that is usually the intuition, right? Rather than complicated math. For the way to do equalization, you just remember 1 times 100 equal to 10 times 10. Then I'm sure you can find the literature to find the details. The coding part is very simple, just a couple of lines of code. You can also reference Qualcomm's AIMET open source tool for those implementations. Okay. So let's continue with another technique. Okay. So adaptive rounding. So quantization loses accuracy. It's all about rounding. Is it optimal if we round individual numbers? Say this is the weight matrix. 0.3 gets rounded to 0. 0.5 gets rounded to 1. And 0.7, 1, 0.2, 0. Is that optimal? Actually, that is not, right? I just care about the individual weight, but actually the weights interact with each other. Okay? So the best rounding for each individual weight may not be the best rounding for the entire tensor. Okay? So we want to do such adaptive rounding. Okay? One potential result for adaptive rounding for this tensor could be actually 0.5 might be rounded to 0 rather than 1. So how do we learn that? So we want to learn such rounding mechanism using a small amount of training data. Okay, almost post-training quantization because it still requires a little bit of fine-tuning. So here is the method. Say we want to choose from either the upper or the lower to get the best reconstruction. We introduce this delta, which ranges from 0 to 1, which is a learned hyperparameter. Okay? We round this W floor plus this delta. Okay? So we want to try to find this V tensor, which has the same dimension as the weight tensor. Okay? And each value is between 0 and 1. And we want to do a function that map the V to the value 0 to 1. Usually it is using this rectified sigmoid. So remember, sigmoid is between 0 and 1, but it doesn't touch 0 or 1. So we want to first make it like minus 0.1 to plus 1.1, and then clip it between 0 and 1, so it can reach either 0 or 1. Okay? So we apply this H function to this V tensor that is going to be learned, and then try to minimize the difference between the original Wx versus this rounded Wx. Okay? Now, of course, we want to penalize this V tensor, okay, by adding this regularization term that encourage this H V function to be binary, either 0 or 1. So using this method, you can give a small batch of images and try to minimize the difference between the original Wx versus the quantized Wx by learning this V tensor. Okay. All right, so that's all for the quantization of the weight. So now let's switch gear to talk about quantizing the activations. So what's the weight difference between the weight versus activation quantization? So for weight, that is static, it's constant, and determine the range at compile time. But for activation, the range for different image, the range might be different. Okay, so that's the difference. So we are going to feed it with a batch of images. So for certain image, it may have a small range. For a certain image, it may have a pretty large range. Okay? To determine the floating point range, we have to collect those statistics before deploying the model. Okay? We want to first gather like 100 or 500 images and collect the statistics. What is the mean? What is the max? What is the average, etc. Okay. So how do we determine the mean and the max, R mean and R max value? Okay. So there are different approaches. One approach introduced in this paper in 2018 is actually using the exponential moving average. Okay, so during training time, you can find the R mean and R max at our current timestamp versus at your previous timestamp. Okay, so we can use such smoothing using such moving average EMA, exponential moving average method, to update the R mean and R max. So we give a batch of image, okay, and calculate that. And second type is actually using a few calibration batch of samples. Okay? They are trained on the P32 model, okay? And we collect the dynamic range on this calibration data set. So there are several ways to calculate the mean and max. One way is actually try to minimize the mean square error between the inputs, okay, and also the quantized input. Okay, so this is the range of the original input, which could be from a super small value to a super large value. And for the quantized value, we may just pick, so we have a limited amount of centroids. For 2-bit, we only have 4 points. For the commonly used 8-bit, we only have 256 centroid. So we have to smartly utilize our resource for this limited number of centroids. Okay. So for this tail, and for the tail over there, we want to cut it. Okay. So everything smaller than this value should be quantized to this value. Everything larger than this value, we should clip it to this value. Okay. So between this and this, we are going to linearly find the different centroids by dividing the range by 256 if you have 8 bits, by 64 if you have 6 bits. Right? So the key problem is really how to find the value here versus the value here for clipping. Okay? There are several assumptions. If the inputs are in, for example, Laplacian distribution, then the Laplace parameter B can be estimated from the calibration of this distribution. Therefore, the Rmax, we can have this pre-calculated value, the optimal value, either 2.83 B if you have 2 bits, or 3.89 B if you have 3 bits, versus 5.03 B if you have 4 bits. Okay? But that's not necessarily the case if our activation doesn't follow this Laplacian distribution. Okay? There's another method which is also widely used by NVIDIA in TensorRT in modern GPUs, okay? So which is using such KL divergence-based method to calculate the boundary. Okay? For example, this is the distribution of the activation value, okay, from 0 to 25,000. Okay? And this is the normalized number of counts. We have a lot of parameters that is super small. And as the value gets larger, there are fewer amount of activations that is pretty large. Okay, so most of the value is pretty small. Only certain activations are really large. So probably we should not find the max to be here because very few activations is actually choosing such a large value. So it's a waste of centroid for us. We may as well put something here, right? So everything larger than this value will be clipped to this value. And since there are not many of such large values, we may find it somewhere closer to the left. But how exactly should we determine this value? Okay, so those are the intuition, but mathematically, we want to quantify this number of this feature by finding this KL divergence, okay, which is measuring the loss of information, okay, which is the relative entropy for this information divergence. For example, if we have two discrete probability distributions, P and Q, one is before quantization, one is after quantization, we want to minimize their KL divergence, which is defined by Pxi times log Pxi over Qxi, and then sum them up together. It's very easy to calculate. Okay? And then we want to just find the location where we can minimize such KL divergence. So the intuition is that the KL divergence measures the amount of information lost when approximating a given encoding. Okay? So this is a given encoding. The approximation is done by two steps. First, clip it, and secondly, discretize it. Okay? We want to minimize before, which is P, and Q, which is after. Okay? The sequence between P and Q doesn't quite matter. So for more information, you can check out this slide from NVIDIA, Tensor RT. This is a very widely used method, and we tried this and actually quite effective by determining the range for convolutional neural nets. So okay, so this is the illustration for the ResNet 152. So this is the distribution of the activation for a certain layer. And then by running KL divergence, we decided to clip it at this location. Okay? So everything above this number is clipped to this number. So that's why you see this new distribution where everything, the amount of everything that is above this number is clipped to this number. And this is the number of weights. It's actually pretty big at this point. So everyone understands this sudden jump? Because everything above this value will be clipped to this value. So there's a sudden increase for the quantity. So here are more examples for different layers. So for AlexNet, ResNet 152, this is GoogleNet. This layer is a bit different from other layers. Okay? It's forming this distribution. Okay? So everything, again, we clip it above a certain value. The clipping decision is made by minimizing the KL divergence. Okay, question?
Is there any sort of methodology for like how you choose this calibration batch, or is that kind of?
Usually it's based on like 100, 500 images. It should be representative for your target task. Like if you are doing autonomous driving, hopefully you can find those rows. And if you are doing like flower classification, you want to find some similar distribution images. All right. Lastly, let's talk about how to quantize the bias. Okay. So quantization will change the distribution, right? So common assumption is that the quantization error is unbiased, meaning that before and after quantization, the mean value should be similar. But actually, according to this study, that's actually not the case. For the original Y output versus the quantized output, actually the difference is actually not around 0. For example, this is the output error. So the distribution, this is showing the distribution of bias output error for each output channel. Okay, so we can see some of the output error could be having a pretty large absolute value, okay, and only a few of them is around 0. So our ideal case, okay, so is by introducing this bias correction term, so that we want most of the output channels could have a 0 biased value after quantization. Biased value means if you feed it with a certain number of images, the floating point versus the quantized value will give you the similar mean. Okay? So how do we do that? It's actually pretty simple. We just run a few batch of images and calculate the difference. Okay, so we introduce this term, which is defined by quantized W minus the original W. Okay, so we absorb this this value into the original Wx, which is the quantized W times x. And we just absorb this bias, the bias parameter into your bias of your neural network. Okay. And also this can be inferred from the batch normalization. Okay. So which is a very simple technique. Doesn't even require actual training data or actual calibration data. You can just infer the bias from your batch normalization term. Okay. In batch normalization, you have a mean, you subtract the mean divided by the variance, right? So you can infer that from the BN layer. And after this bias correction, so for all the channels, the error will be around 0. All right, so here's a summary for post-training int8 linear quantization. What is the accuracy for different scenarios? So we have the activation quantization, weight quantization, and below is showing the accuracy. For activation, we have symmetric and asymmetric, right? Really like the tail divergence or using the EMA approach. And for the weight, we also have asymmetric and symmetric quantization. We have per tensor, we have per channel different quantization strategies. And here on the right-hand side, we have weight equalization or not. And we can observe for most of the large neural nets, Google net less than 50, less than 152, a different quantization approach, they can all lead to pretty low drop of accuracy, no matter if it's symmetric or asymmetric, if it is per tensor or per channel. Okay? So the critical point is really such compact neural nets, which we're going to introduce in the neural architecture search session. So for mobile net, like if we use this asymmetric per channel quantization, the loss of accuracy is actually pretty significant. But if we switch to such asymmetric per channel quantization, that can get better. Okay? But really, if we use weight equalization, it can further reduce the loss of accuracy, showing that such weight equalization method plus its bias correction is actually quite helpful. But in general, can we recover such loss of accuracy from training? So far, we didn't do any training to recover the accuracy. But like in pruning lecture, right? In pruning lecture, after pruning, we can recover the drop of accuracy by fine-tuning the remaining weights. Okay, so can we further fine-tune the remaining quantized weights to recover the accuracy? Okay. So we want to recover the accuracy. Okay, recover the accuracy after quantization. So let's first look at what happens after quantization and how do we modify the data flow to train a quantized neural net. Okay. Okay, so we want to flow the gradient back. So this is the input, okay, and we have the weight. After quantization, we feed it to this layer by convolution, batch normalization, and redo, which becomes the output. So this is the input, this is the output. And during feed forward, this is the direction. During back propagation, this is the reverse direction. We want to flow the gradient back to the input we also want to flow the gradient back to the weight. Okay? For this k-means quantization method, we briefly alluded that in the last lecture. We can calculate the gradient using the centroid as the input, and we calculate the gradient. We match them using the same color, which is basically according to the index. Okay? This is for the first centroid corresponding to this gradient. And this is the second centroid corresponding to this gradient. Okay? And finally, we reduce either by summing them up together or finding the average about the gradient, and we multiply it by the learning rate and subtract it from the original centroid, which becomes the fine-tuned centroid. Okay. I also experimented. So this is first of all fixing the cluster index, assuming this weight is always associated with the first centroid, but the centroid can change. I also actually experimented whether we can also learn this index, but we find the difference is very minimal compared with fixing the cluster index for such 4-bit or 8-bit quantization. So what about the linear quantization? Okay, not the k-means quantization. Okay. So we have this activation quantization function. Okay. Remember, we have this scaling factor. We also have this 0 point for the activation. So what we do is actually this simulated or fake quantization, okay, which maintains a full precision copy of the weight, okay, throughout the training. Okay. So such that this small gradient can be accumulated in a very fine-grained manner if we have this full precision value in the back. Otherwise, if we imagine we only have like 2, 3, 4, those integer values, it cannot capture very little gradient change. Like 2, we added the gradient becomes 2.1. After quantization, it becomes 2 again. So you do not cannot capture those large enough changes. Say after 10 steps, it becomes 3 or 2.5. You cannot capture that if you don't have this full precision copy of the weight in the back. So during fake quantization, we maintain this full precision copy of the weight in the back. Okay, so if it is 2 and you get updated to 2.1, you still have this 2.1 in the back. But after quantization for feed forward, it is 2 again, right? So this is the quantization part for the weight. Actually, that corresponds to the scaling factor times original integer weight, but we are not maintaining this integer weight in the back. But actually, we are maintaining the floating point version to simulate such quantization procedure. Okay. Similarly for the activation. So let's see how do we update this linearly quantized weight matrix. So first of all, we do such affine transformation. So this is the QW, okay, which is the integer weight. And this is the W, which is the floating point weight that we are always maintaining in the back. Okay? So this is a quantized W. This is this fake quantization where you want to recover from your quantized weight. Okay? You subtract from the 0 point, you scale it, okay? And this is the recovered weight. Okay? So this is the quantized weight, and this is the full precision weight in the back. And you can see they are actually quite similar. But both of them are represented using floating point number, okay? So that we can capture the small gradients. Okay? And this procedure simulates the disturbance, this change of the quantization procedure. So for example, 2.09 actually becomes 2.14 in this case. So back to our discussion about the quantization graph. So we maintain this floating point a full precision copy of the weight in the back so that we can accumulate this small gradient to this W. Okay? And also similarly for the activations, okay, we maintain this floating point copy, which is simulating this quantized version minus the 0 point times the scaling factor Okay? So these two operators are the two actual operators on top of the original computational graph. Okay? So when we are doing back propagation, we have to figure out how to propagate the gradient through this activation function and through this weight quantization function. Okay? So through this activation quantization function and this weight quantization function. This is actually non-trivial where if you calculate the operator for either the weight quantization or the activation quantization, they are actually step function. Right? So everything between 0.5 and 1.5, they will be quantized to 1. Okay? So the slope of such quantization operator is actually 0 everywhere. Right? So the quantization is discrete values, and the derivative is 0 everywhere. Okay? So we cannot backpropagate the gradient. How do we solve this problem? We actually use this widely used STE, which is straight through estimator. Okay? We just assume this partial QW over partial W is just 1. Okay? So that we can directly calculate the gradient with respect to the quantized weight to be as if there is no operator right here, straight through. We just pass the gradient straight through this operator as if this operator is an identity operator. Okay? So that's a widely used approximation straight through estimator when we are doing backpropagation for the weight and for the activations. All right, so this is the big picture when we are backpropagating the gradient through this weight quantizer, through this activation quantizer. We just pass the gradient straight through this operator without worrying about the gradient impact. Okay, so this is the accuracy for post-training quantization versus the quantization-aware training. And we can see quantization-aware training can drastically improve the accuracy compared with just doing post-training quantization. That's it.
Are there other estimators for passing the gradient through a quantizer, or is it always straight through?
For other estimators, I'm not aware of. So straight through is the most popular estimator. Maybe there are other nonlinear or more complicated schemes. So yeah, that could be something you could decide on yourself. But so far, the most popular is just straight through estimator.
To answer that question, for binary, I've seen people using hyperbolic tangent, and people have used that for ternary as well. So I guess that's an alternative.
For binary and ternary neuronets. Okay, that's a good point. Okay, so so far we get the effect of post-training quantization versus quantization-aware fine-tuning, and we find actually, especially for these per tensor operators, quantization methods, the recovery of accuracy is actually quite well, almost recover the full precision accuracy. So this is showing the floating point accuracy versus 8-bit quantized accuracy after the fine-tuning. Very close, and this is showing the latency reduction from about 15 milliseconds to only about 6 milliseconds while maintaining the accuracy. This is running on the Snapdragon 835, which is actually pretty old. After Snapdragon 835, we have 855, 865, and after Snapdragon 855, we introduced this HTP, which is specialized accelerator, which make it even faster. So nowadays, to achieve 75 top-out accuracy, that's way below 1 millisecond. So that's how fast this area is moving since 2018. All right, so far we talked about Canadian quantization, linear quantization, and just now alluded to those even fewer number of bits, which is binary and ternary quantization. Okay, so we are going to introduce how do we use even fewer number of bits to represent neural nets. But before that, I want to give tell a fact that when you are reducing the precision, say from 8-bit to 4-bit, you reduce the amount of storage by half, right? But the complexity of the multiplier is also actually quadratic. So you reduce the computation more than the reduction of the memory movement. But actually, memory movement is much more expensive than computation, right? So it's debatable whether it is worthwhile to go with even lower number of bits. Right? So that's something to think about. You're reducing your memory movement by half, but you are reducing your computation by 4 times, right? So is that a worthwhile decision? That's something we need to think about. Okay, so let's talk about binary and ternary quantization. Can we further push the quantization precision to just 1 bit? So we have 3 rows. First row, both the input and the weight is real number. Okay, so we assume the memory everything is 1. This is a matrix vector multiplication. This is the weight value, and this is the activation. We just run this weight times the activation in the conventional manner. And what if we have the weight to be binary? Okay, meaning that we have either +1 or -1 for the weight. Okay, so that becomes 5 minus 2, 0, and -1. Okay? So the memory would be, so the operation will be limited to just plus addition and subtraction, since there is no multiplication anymore. So the memory is 22x less for the weight, and the computation is about 2x less. Since we don't need to do multiplication, only accumulation. Okay? And when we are doing the binarization, there are 2 approaches. One is just look at the sign. If it is a positive number, then we make it to be +1. If it is a negative number, then -1. There's a better approach, which is doing stochastic binarization. Okay? Saying that it's not deterministic, but depends on your value. If it is closer to a larger value, then we have a higher probability to quantize it to +1. If it is a smaller value, then we have a higher probability to quantize that to -1. Okay, so this is the quantization function. So turning point is -1 and +1. It ranges between 0 and 1. Okay? But it's difficult to implement in hardware because we need some random number generator. But if you have a full circuit that can easily do random number generator, this could be used. Okay, so let's give a concrete example. So this is our familiar 4x4 matrix. If we binarize that, we can just look at the sign. If it is positive, then it's +1. Negative it is -1. Okay, so the distance between these 2 matrices is 0.28. So that's called binary connect. Actually, we lose a lot of accuracy. This is very simple, but we lose about 20% accuracy. And we can do better by introduce this scaling factor. Okay? So we calculate the average of the absolute value of the original matrix. So it's 1/16, since it's 4x4, times the absolute value. Okay? It turned out to be 1.05. Therefore, we just reconstruct it by alpha times this binary matrix. Okay? And just using this very simple technique can actually improve the accuracy. Actually, 0.2% better than the original net, which is quite interesting. Okay, so what about if both the weight and the activation is binary, either +1 or -1? So we can do even simpler calculation. So let's see how does it relate to the XNOR operation. So this is the truth table for the weight for the activation. 1, 1 is 1. 1 minus 1, multiply them together is minus 1. Minus 1 minus 1, the multiplication is plus 1, etc. Okay? And if we map this minus 1 to be 0, okay, if we map all the minus 1 to be 0, actually we find it matches perfectly with the XNOR function, where if both of them are the same, then the output is the same. Both of them the same, output is 1. Okay? If one of them, if they are different, then the output is 0. If they are different, the output is 0. Okay? So such binary multiplication maps perfectly well with the XNOR operation. Okay? Therefore, we try to use the XNOR operation, which is bitwise operations, is very cheap, to replace such binary multiplication. Okay? So let's try to calculate the XNOR of these two arrays. 1 times 1 becomes 1 XNOR with 1. And unfortunately, the final result doesn't match. This is plus 1, this is minus 2. So what is missing to try to match these two results?
We must replace the zeros with minus 1 again.
The 0 with minus 1 again. Right. So the 0 here actually means minus 1. Right. So there is a bias term. Right? So actually 0 actually means minus 1. So whenever you see 0, actually that is minus 1. Okay? Whenever you see 1, actually that is actually 2 more than the original value. Okay? So you just assume if everything is minus 1, which 0 represents that, like I mentioned, that is minus 4. And then we count how many 1s are there. If we have just a single 1, then we plus 2. If we have 2 1s, then we plus 2 times 2. Okay? So we count the number of 1s in this array, multiply that by 2, and then add to this like minus n, which is the final result. Okay, again, assume everything is 0, then it should be minus n. Okay, we have n elements, everyone is minus 1. Then you count the number of 1s in this array and multiply by that 2 and sum them up together. So let's see, this is the final equation. Assuming if everything is 0, then since 0 is representing minus 1, then this is minus n if you have n elements. Okay? And then you count the number of 1s in the result and multiply that by 2. So this is counting the number of 1s in this array, okay? Which is basically a pop count operation. Pop count is very easy to implement. Given a stream of 1s or 0s, you count the number of 1s in this stream, okay? Returning the number of 1s. Okay? So the final result becomes minus n times the number of 1s in this array. What is this? Multiplied by 2. Okay? Which are all very simple to implement. Any questions so far? Why XNOR becomes this simple equation? Okay, good. Let's give an example. This is 1 minus 1, 1 minus 1, which is actually 1, 0, 1, 0. So this is 1, 0, 1, 0. And activation is 1, 1, minus 1, 1. Actually, it's 1, 1, 0, 1. Okay? So 1, 1, 0, 1. We first XNOR them together, count the number of 1s, which is just 1. Okay? We have a single 1. And then multiply by 2, and then add to this minus 4. Okay? So we get the result minus 2, which finally matches our original value. Okay? Remember, our original value is also minus 2. So this is very simple to implement in hardware. We can do these bitwise operations. Actually, I and Eugene implement that in our FPGA within a day, which is pretty simple. So let's see what is the accuracy impact for such algorithms. So for AlexNet, GoogleNet, Zen 18, using these XOR operations for all these scenarios, it can have okay performance. Think about like 5 or 6% drop of, so here is about 12% drop of accuracy, and X norm is about 18% drop of accuracy. Okay? So you cannot get very, it's okay accuracy, but not perfect. Right? But considering you are saving a lot of memory for the wait and activations, and only 1 bit is required for the wait and activation. That's still pretty awesome. Maybe helpful for some non-safety critical IoT applications. So, since the accuracy is not perfect, can we introduce one more weight, like 0, from ternary to from binary to ternary, to try to recover some accuracy, right? So instead of use just +1 and -1, let's introduce a third centroid, which is 0. Remember, a lot of the weights is centralized around 0. So we try to have better accuracy by introduce another value, which is 0. So the new rule becomes that if it is greater than the threshold, that is positive RT. If it's smaller than negative delta, then it's minus RT. Somewhat in between becomes 0. Okay? So empirically, we set this threshold by 0.7, which is an empirical value, times the expectation about the weight. Okay? For example, given this, our familiar weight matrix, we calculate the delta to be 0.7 times the average of the 1 norm, okay, which is 0.73. Okay? So everything larger than 0.73, like this one, will be quantized to 1. Everything smaller than minus 0.73 will be quantized to minus 1. And like something between minus 0.3 and plus 0.3 will be quantized to 0. Okay? Question?
Oh, where does the 0.7 come from?
This is an empirical value coming from this paper, showing that empirically, if you see the mean times 0.7, that's a good point to estimate the threshold. Okay, and if we calculate the 1 norm for those non-zero elements, okay, so they are all together. This is the number of non-zero elements, and then divided by 11, we get 1.5, which is the scaling factor. Okay. Since they are all together 16 elements, right? 1, 2, 3, 4, 5. 5 of them are 0, okay? So actually there are 11 of them that is non-zero. And we calculate our norm corresponding to those non-zero elements, so we can calculate the scaling factor. Okay, so we can quantize that into this matrix, which has only 3 elements, positive 1, minus 1, and 0. And with the scaling factor, 1.5. So using this ternary weight network, we can recover the accuracy from 60 to 65. Okay, it's closer to this original like 70 top line accuracy for resident 18. So far, so good.
If it's using 2 bits, isn't it better to use 4 numbers instead?
Right, exactly. We are actually wasting 1 bit since we have only 3 centroids. But actually using 2 bit, we can represent 4 numbers.
So I think the reason that Trenary only uses 3 values is because of hardware implementation. 3 bits is like 3 values in the maximum that can be done without well, I forgot if it's more complicated multiplier or whatever. But
Yeah, the reason you still use ternary, although you lose 1 centroid, is that for 0 multiplied by anything is still 0. So you can potentially skip the 0 multiplication. And also by having this symmetric characteristic, we can turn multiplication into addition and then do just one single multiplication, like a single scale factor. So that's the advantage for having such symmetry and also having the 0 as one of the centroids. All right. So far, we talked about the mean, the positive value and the negative value. They are both fixed. Okay. What if they are trainable? So that becomes this trained ternary quantization, which I worked on actually 5 years ago. I was working on that project. So again, we have this delta. Everything above this delta is positive, but the value can be trained. Rather than 1, it becomes WP and minus WN. And they can be different, right? So given a full precision weight, okay, we first normalize that between -1 and +1, and then we quantize that according to this threshold. Okay? Everything in between is 0, above is 1, below is -1. And then we can train this scale factor, okay, so that we can have a different positive and negative values. So by allowing such flexibility to have different WP and WN, we can actually further recover the accuracy, okay, from 65 to 66. So now we have a whole family, okay, from this floating point to integer index, floating point codebook, fully integer weight to this binary, and ternary weights. So nowadays, probably the most popular still is linear quantization. And lastly, several hardware like NVIDIA GPUs nowadays support different precisions, 16-bit, 8-bit, 4-bit, etc. So mixed precision quantization is becoming quite popular. So compared with uniform quantization, where both the weight and activations are quantized to, say, 8-bit, now we can allow different precisions for the weight and for the activations. For different layers, they are also different. Right? For example, the first layer sometimes is more sensitive. We can use P16. And some of the middle layers, less sensitive, we can use integer 8. Right? So the next question is, this is a pretty big design space. We have 8 choices for the weight, 1 to 8, 8 choices for the activation. For each layer, we have 64 choices. If you have n layers, design space is 64 to the power of n, which is a pretty huge design space. So how do we deal with that? So 3 years ago, we published a paper using RL, reinforcement learning, similar to the AMC method, to figure out what is the sparsity ratio for each layer. This is figuring out what is the number of bits for the weight and activations for each layer. Okay, so we have an action critique model. The action is basically the number of bits for each layer. The reward is basically the number of bit ops together with the accuracy. And for the environment, we plug in the hardware simulator. Given a precision, we get the feedback, which is a combination of accuracy, a combination of latency and also the energy. Right? So compared with uniform quantization, by using such non-uniform quantization, we can have a better latency and accuracy trade-off curve. Okay? And we can also tune not only the model size, but also the latency, even the energy. Okay? So given a certain energy constraint, say we are running out of battery, we can have a much better trade-off using the same amount of energy, but have higher accuracy in this case. And here are some interesting findings for the cloud device and for the edge device, for the weight and also for the activations. How many bits are allocated? For example, on the edge device, we find the depth-wise layer are allocated with fewer number of bits, and those point-wise layers are allocated with more number of bits, and forms a clear pattern with depth-wise, point-wise, and point-wise, depth-wise, and point-wise for mobile 92, showing that the RL agent is actually learned something. Okay, so that's the summary for today's lecture. We first reviewed the linear quantization, and then we talk about both post-training quantization, which is super popular. If you have just one take home from today, just make sure you get the post-training quantization techniques are learned, and we are also going to cover that in the lab 2, which we released today. Also, we talk about quantization-aware training to fine-tune to recover the accuracy using this straight-through estimator. And then we talk about some fun stuff like binary ternary quantization meets precision quantization. Okay. So lab 2 is out today. You can access the core lab using the similar approach as lab 1. It includes the basic concepts of quantization, k-means quantization you're going to implement on yourself to see how much can you quantize without losing accuracy. Also, we can you will do such quantization-aware training to recover the accuracy, and then you are going to implement this linear quantization following those equations. So, give you a step-by-step instruction, integer-only inference. Okay. And this could be a starter code for other innovations that can lead to your final project. Okay. All right, it is due on mid-October. Hopefully, give you enough time to finish the lab. Okay, feel free to contact us during the office hour, which is Wednesday. And thank you. This is the end for the basic lecture.